This tutorial is just to go over what I lectured about in class today. Probably what I think is one of the more challenging things to wrap your heads around is this idea of gravitational potential energy when G is not a constant anymore. And this leads us to being able to derive an expression for the escape speed. So the escape speed is the vertical speed I'd have to launch something in order for it to escape the gravitational pull of the planet. So we have to use conservation of energy plus kind of a redefined version of this. So this, as we know, is good near the surface, but what if we start moving out to infinity? If we recall from Newton's law of universal gravitation that we can calculate the gravitational field strength by taking the universal gravitation constant and then I multiply it by the mass of the Earth or the planet, and then I divide it by the distance squared, the distance from the center of mass. So we see as we move further and further away, as this value of r approaches infinity, well, G is going to go towards 0, which leads us to what we generally accept are boundary conditions for energy in physics, is that the gravitational potential energy goes to 0 as r goes to infinity. Okay, so it is generally accepted in physics, and you'll find this on your equation sheet, that the gravitational potential energy is equal to minus big G, mass of the Earth, times the mass of the object, divided by that radius. So this is kind of where and what you'll find on your equation sheet. What I want to do is explain to you where this negative sign comes from and why it makes sense to have it there, and that's the challenging part. So where did this come from? Well, if I take m times g times h, and that's my gravitational field, I'm going to use this value for g in there, and then the h, if I just let h equal r, then the r's will cancel out, and then that's the m is that m. So that's where that came from, but I need to explain where this whole negative sign comes from. All right. So there's two things that we start off with, and one I've already mentioned, is that we're going to let gravitational energy equal 0 at a radius that approaches infinity, or is at infinity. And this is just a standard physics boundary condition that we use. The second condition, to help us explain it, is just to point out what you may or may not have noticed as we started doing all those bar chart graphs, that the work done by gravity is going to be equal to the negative change in gravitational potential energy. And I want to explain that a little bit more. So, all right, so let's just look, before we start moving out to infinity, let's just look at where this came from, just as a reminder. So if I have an object here, and it starts at gravitational initial of equal to 0, and then I lift it up some displacement to this location, it's going to have some final gravitational energy, and I'll just say it's equal to U times G. Well, I know that the work done by gravity has to be negative, because as I'm lifting it up, the force of gravity is going to be opposite to that direction motion, so I know it has to be negative. Now, if I look at the change in gravitational potential energy, which is always equal to the final minus initial, that's standard physics, it's always final minus initial. My final gravitational energy is UG, my initial is going to be 0, so I get a positive value here, so hence, if I know the work done by gravity is negative, that's where this negative sign comes in here. So the work must be negative so that I know that I have negative work by gravity when I lift something up. Okay. Similarly, if I take the same box and now I drop it, its initial gravitational energy is going to be UG, and then its final gravitational energy would just be 0. I know that the work done by gravity must be positive, again, because the force of gravity is in the same direction as my displacement. So if I calculate my change in gravitational potential energy, final minus initial, my final gravitational is 0, my initial I'll just call UG, but I know the work has to be positive, so then I get that negative sign again in front, so that it's all consistent with what we do near the surface of the Earth. When we start going out to infinity, we have to kind of understand that this is how we define work done by gravity. It's equal to the negative change in gravitational potential energy. All right, so moving on, we got the foundational pieces done. Now we're going to start moving out to infinity. All right. Okay, so let's say here's our planet, and here is my object right out here. And out here we have our boundary conditions that r is equal to infinity. Our gravitational potential energy is going to be equal to 0. Okay. If I understand the work done by gravity is equal to negative my change in gravitational potential energy, that means it's going to be negative my final minus my initial. So I'm doing the same premise here. Now I'm going to substitute in kind of our condition here, minus our final gravitational energy at the surface of the planet is going to be g times the mass of the Earth times the mass over the radius, minus my initial was equal to 0. So I get that the work done by gravity is going to be a positive, because I have a negative times a negative, g times m times r. So if I have positive work done by gravity, that means that I'm going to have a positive change in kinetic energy. So as my object falls towards the planet of the Earth, it's actually going to increase speed, which physically just makes sense. So in this way, I'm hoping that I can explain not only why there's a negative in front of here, but also why there is a negative in front of there. So what does this look like on a graph? On a graph, what does that look like? Okay, so one thing that we understand, like as we lift an object up, its potential energy increases, so we've kind of played with that just near the surface of the Earth. We know that is true. So if we lift something out to infinity, we would think that our potential energy is also going to increase. So if our potential energy starts out negative, it's going to increase to 0 as it goes out to infinity. So it kind of, again, is consistent with our thinking of increasing potential energy. So what would the graph of our potential energy look like? Let's just draw a sketch here. So let's make on this vertical axis, I'm going to graph the potential energy. And along this horizontal axis, I'm going to graph the distance that it's carried away. So let's make this point right here is going to represent the radius of the Earth. So at that location on the surface of the planet, the potential energy is going to be negative, and it's going to be equal to the minus g mass of the Earth times the mass over the radius of the planet. So that's the value right there, and then it is going to increase to 0. It's going to go as that 1 over r squared function, the negative 1 over r squared, so it's going to increase asymptotically towards 0 gravitational potential energy. So that's what the graph would look like. So this negative potential energy is indicative of what we call a bound state. That means that the object is, this object right here, is trapped within the gravitational field of the Earth, and it's not going to be able to escape that gravitational energy or break away from it until it has enough energy provided. So this negative potential energy, is indicative of what we call a bound state. And this may sound familiar, is a similar kind of idea in chemistry when we talk about the bound energy states of atoms. Okay, so this leads us to our explanation of escape speed. All right, and this is ultimately where we wanted to be. So escape speed. Escape speed means that we want to have sufficient vertical velocity in order to escape the gravitational pull of a planet. I'm writing that all down. All right, so in order to go through that derivation, basically what we're going to employ is the idea of conservation of energy. And this is why this sometimes fits in when we're talking about Kepler's laws and orbital motion, but it really is a conservation of energy principle, and that's why I kind of table it until later. Basically, our initial state is going to be on the surface of the Earth, or the surface of the planet. Our final state is going to be at infinity. Okay? So conservation of energy, if in the absence of air resistance, which is what we're going to consider, is going to be the sum of our total mechanical energy of our system before is going to equal our total mechanical energy of our system afterwards. Mechanical energy, if you recall, is just going to be our kinetic energy, so our initial kinetic energy, plus our initial gravitational potential energy, that must be conserved, so my final kinetic energy must equal my final gravitational potential energy. So initial gravitational energy is going to be 1/2, m would be the mass of the thing you're trying to launch, times the escape speed squared, plus this initial gravitational energy on the surface of the planet is going to be minus g, mass of the Earth, mass of the object, divided by the radius of the Earth squared. Remember, I'm launching it from the surface of the Earth. Now at infinity, as an object is launched up in the air, that speed is going to approach 0. When it gets to infinity, the kinetic energy will go to 0. And then also our assumptions that at r equals infinity, the gravitational potential energy at that point will also go to 0. So this is just equal to a big fat 0. Now I'm going to just solve for escape speed. Now it just becomes algebraic. So 1/2 mass the escape speed squared is equal to positive g, mass of the Earth, mass over the radius of the Earth squared. I'm going to cancel the masses out, and I'm going to solve for the escape speed, which is going to be 2. Take the half over there. Mass of the Earth divided by the radius of the Earth. Oh, I forgot a g. G goes in there too. Ooh, meg. And then I take the square root over the whole thing. More commonly, it's written this way with the g first. I don't know. Whatever. I forgot it. Okay, and that is going to be our escape speed. So it's a pretty quick and easy definition, but one needs to understand this negative sign near at the surface there. The gravitational potential energy is going to be negative, and it's this expression right here, which comes from Newton's law of universal gravitation, as well as our understanding of this guy, plus Newton's law, and then standard kinetic energy, and then these fundamental principles that the gravitational energy is 0 at infinity, and that my kinetic energy also, it will slow down as it gets further and further away from the planet. So that's it. Hopefully this was helpful.